We've already done some work graphing polar equations by plotting points, but there is some fine tuning we can do. Let me give you an equation. And then just as in algebra, there are a couple things we can do to check and see where there are some critical points. So if the whole thing is equal to 0, then we get 0 equals 5 minus 5 sine of theta. Subtracting 5 from both sides gives me this. And then I'm going to divide both sides by -5. And I get 1 equals the sine of theta. Another way to write this would be the sine of theta equals 1. And we know where that's true, right? Since we have x, comma, y, and these are sine values, then on the unit circle, this point right here, is where this equation is true, and that's at pi over 2. So theta has to equal pi over 2. And that means the radius of the circle, which I replaced with 0, the radius of the graph is equal to 0 at pi over 2. Let's make a note of this. My input values are thetas, but we write r comma theta, so I'm going to put theta over here, and I'm going to put r here. I'm going to make a list of input values here and output values here. Your book reverses this. They have theta here, which is kind of intuitive. You know, we're used to having x, which is all our inputs, and they spit out y's, which are all our outputs. In this case, I have my inputs in this column, which is reversed from how I've done it in the past, and my outputs over here. It doesn't really matter. Use whichever is convenient for you. When r is theta, when my output was theta, I found that happened at pi over 2. And I got that not by plugging pi over 2 into the equation. I would have eventually figured out that the 5 minus 5 times the sine of pi over 2 would be 0. But I didn't need to. I just kind of used a little bit of algebra instead. You may find that there is more than one 0 in some of these graphs, so keep that in mind. If the equation that you're solving over here has two solutions, then there are two angles for which the radius is 0. That can happen. Now let's take a look at some extreme values. Where does sine hit its maximum value? If we graph it like this, this is pi, this is 2 pi, this is pi over 2, and this is 3 pi over 2. So by way of reminder, this is when theta equals 0, the input is 0. This is just for y equals the sine of x, or I could write this as r equals the sine of theta, just for fun for right now. Sine finds its maximum value at pi over 2. When we plug pi over 2 in here, we get 0 out. It finds its minimum value at 3 pi over 2. When we plug in 3 pi over 2 here, we get -1, but when we plug 3 pi over 2 in here, 3 pi over 2. Now I have to do some arithmetic. I have r equals 5 minus 5 times the sine of 3 pi over 2. And I know what the sine of 3 pi over 2 is. It's -1. So that makes this equation r equals 5 minus 5 times -1, or 5 plus 5, which is 10. So the maximum radius is 10, and it occurs at the angle 3 pi over 2. Now, that's pretty much it for this section, but we haven't actually graphed anything yet. So let's make a point of finding a few other values. Some common values are always good. 0, pi over 6, pi over 4, pi over 3. I'm going to use this same function here, but with different values in for theta. I'll go get those and show you at least a few of them in just a minute. Notice that with the exception of this this angle right here and these two quadrantal angles, which are the extremes of quadrant 1, with the exception of this, all of these angles are in quadrant 1. So we'll probably need at least a few from quadrants 2, 3, and 4 as well. Most of that I'll do off screen. And then we may want to check this graph for symmetry as well. That may actually save us from having to graph a whole bunch of points. So that's where the symmetry thing can come in handy. So let me go get the values that go with these theta values. All right, I did that a little out of order. It seems a little out of order because I didn't have my recording queued up. So I thought I had put these at the end of that last piece. But anyway, here they are. We have some values. Now remember that this is my input column and this is my output column. So pi over 2 comma 0 is going to be here because it's got a radius of 0, right? 3 pi over 2 is this angle here, so it's on this line, and my radius there is going to be 10. I have 1, 2, 3, 4, 5, 6, 7, 8 lines here, so I'm going to let each one of these be 2. 2, 4, 6, 8, 10. Otherwise, I won't have enough room to graph the whole thing. 1, 2, 3, 4. So that is going to be there. I'm going to mark that and remind myself that that's a 10. So I've done this one and this one. 0, comma 5. So I'm going to go around 0. It's like I'm not going to move around there, but I'm going to go out 5. And that's 2 fourths. So that's about here. And then 5 halves pi over 6. Sorry, pi over 6, 5 halves. So starting here, I'm going to go out to pi over 6, and then I'm going to go out 5 halves. Well, this was 5, so half of that. 5 halves, you can think of 5 halves as 2.5, so I'm going to go 1.25, 1 and a quarter. So I'll be right about there. And let's see, now I've done that one and that one. Pi over 4, 1.46. These could be found relatively easily. I know that this is 1/2, and that's going to make that 5 times 1/2, which is 5 halves. 5 halves is, sorry, 5 is 10 halves. 10 halves minus 5 halves is 5 halves. So that's how I found those all, just sort of mental arithmetic. These ones were harder because they had square roots in them, and in their signs, right? I took the sine of pi over 3 and it had a square root in it, so I had to use the calculator for these two values. At pi over 4, I'm on this line right here, so I'm going to go out 1.46. Remember, my units are 2 here, so this is 2. 1.46 is about here, actually. Nope, it's more like here. There we go. And then at pi over 3, which is this line, I'm at 0.67, so not even 1. If this is 0 and this is 2, here's 1, that's halfway, so I'm going to be here, right about there. And I can't really speak to this point yet, but for the others, I'm starting with, let's see, my smallest input value is 0. My next smallest input value is pi over 6. I'm going to go at 0, 5. I'm going to start here, and then pi over 6, this point is next. And then pi over 4, this point is next. So I'm going to graph something that looks kind of like that. Let me try that again. I missed some of my points. There we go. So this part of the graph looks something like this. Now, we're going to need more points if we want a complete picture of this graph. And there are a couple different ways we could go about that. One would just be to completely just keep plotting points. Like keep finding values. We're going to need values in quadrants 2, 3, and 4. Find theta values, crank out R values from that, and then eventually plot the points. Something we might want to consider, though, is running some of these symmetry tests. I don't want to have to graph all of these points, and all of these points, and all of these points, and all of these points. Well, I'll graph them, but I don't want to have to compute all of these values if I only have to compute half of them. So I'm going to start by rewriting the equation. R equals 5 minus 5 times the sine of theta. And I'm going to start by replacing just the r with negative r. And if I do that, I get, now I'm going to multiply through by negative 1. So I get r equals negative 5 plus 5 times the sine of theta. And that is not equivalent. So that means that we do not have symmetry across this line here. In other words, we don't have a reflection in this half of the circle from what we see in this half of the circle. All right, let's do the next test. Let's replace, I'm going to erase this result here. Let's replace just theta this time. So I'm going to rewrite r as positive r, but I'm going to write theta as negative theta. Now, recalling that the sine of negative theta is equivalent to negative the sine of theta, because sine is an odd function, I'm going to write that this way. And that gives me 5 plus 5 sine theta. And that is not equivalent either. So we do not have polar axis or x-axis or horizontal symmetry. In other words, we do not have a reflection down here of what we see up here. The last test requires, first of all, we'll erase this result, that I replace both r and theta with their negatives. So I'll do that like this, and then I'm going to rewrite this as negative r equals 5 minus 5 times, the sine of negative theta is negative the sine of theta. And that's going to be 5 plus 5 sine theta. Now, let's see, I'm going to go up here. This is a little weird, but I want to, I'm running out of room, as usual. So that means that I can, if I multiply through a negative 1, I get r equals negative 5 minus 5 times the sine of theta. Now, on first glance, it looks like that's not equivalent, which means that we don't have a reflection on this side of what we see on this side. However, it turns out that these are actually equivalent. I can't just multiply through by negative 1 the way I've been doing and end up with the exact same equation, the exact same expression. So they're not equivalent in that way. But let's take a look at what happens when I plug 0 in, not into this equation, but into this equation. The sine of 0 is still 0, and I'm going to get 5 times 0, which is 0, and negative 5 minus 0 is negative 5. So for my new equation, I get not 5, but negative 5. So that's going to be here. If I plug in pi over 6, again, not into the original equation, but into this new version of it. I think at this point I'm going to turn this around. I'm going to erase this work, but know that this result came from replacing both negative r and theta with their negatives. So now if I plug pi over 6 into this equation, I get 5 halves. But if I plug pi over 6 into this equation, I get negative 5 minus 5 times the sine of pi over 6, which is a half, which is negative 5 minus 5 halves, which is, let's see, negative 10 minus negative 15 halves. So now I'm going to stretch a line across what should be the pi over 6 guide line into both quadrants, quadrants across from each other. And I'm going to try to plot the point pi over 6, negative 15 halves. Remember that, let me write that down here, negative 15 halves. So I'm going to start here. I'm going to go out pi over 6, and then from the center, I'm going to go out 15 halves, which is 2, 4, 6, 15 halves is 7 and a half. So 2, 4, 6, there's 8, there's 7, there's 7 and a half. But it's negative 7 and a half, so I actually need to go this way. 2, 4, 6, there's 8, there's 7. That point will go right there. 2, 4, 6, 8, 7, 7 and a half. And now I'm going to delete the guideline, and we can see that that point is sitting right here. Now, we did find a minimum value of 10. That was really a lot earlier work. It's kind of interesting to see that this graph seems to be going like this, and this graph seems to be going like this. I think if I did one more value here, we'd see what was going on. Let's do pi over 3 for this equivalent function down here. So I'll erase this. And I'm going to replace theta with pi over 3, which will give me negative 5 minus 5 times the sine of pi over 3, which is negative 5 minus 5 times the sine of pi over 3 is the square root of 3 over 2. This is going to have to be a decimal thing here, so I'll go get the decimal for this. It's about negative 9.3. So at the angle pi over 3, let's go ahead and put a line in so we can see what we're doing. Pi over 3 is this line right here. And we want to go out to pi over 3, and then starting at the origin, go back 9.3. So that point is going to go 2, 4, 6, 8. That would be 10, that would be 9, so it's just a little bit more than 9. And then at the next value, we're going to hit 10. So let's get rid of our guideline so we can see what's going on. And I'm going to trace this curve around, and we get that. Now, what you can't really see here is that we're using the same input values, and we're getting output values for our positive 5 minus 5 sine theta in white, and R values for our negative 5 minus 5 sine theta in green. And it turns out that those are the same values that you would get, not in the same order, but you would get those in, let's see, 9.3, where did that come in? I don't see it. But you would get those same values on the other part of the curve here, and you're going to get these values here by plotting in quadrant 4. So this does actually have symmetry about the line y equals pi over 2. R equals pi over 2. It just, you can't see it. It's not obvious. That's the main reason I didn't put too much of a focus on symmetry. It can be useful sometimes. Sometimes the symmetry is there, but you can't see it. In the same way that we couldn't really see it in the equations, right? This equation does not look like this equation. You can't really see it until you start graphing, and then you're graphing the negatives of the... Anyway, so we did get some practice not only determining what points were, but then also plotting those points. I think I'm going to leave the rest of this exercise for class. This graph is called a cardioid because it looks kind of like a heart. You could try graphing this in Desmos. Just type in R equals 5 minus 5 times sine, S-I-N, and then type the word theta, T-H-E-T-A, and Desmos will turn that into the symbol theta, and then it'll graph it for you. Try graphing both that and R equals negative 5 minus 5 sine theta. Then change the period over which you're plotting them from 0 to 2 pi to 0 to pi, and see what happens to the two graphs. It's really quite interesting. They are equivalent, and you can see that in Desmos. Now, we're going to work on this in class by hand because I do want you to continue getting practice, but we do have powerful tools that will help us see what these graphs look like as well. So these two things in tandem, I think, are great. Now, the rest of this subsection is very, very long, but the subtitles, if you were, are things like investigating circles and investigating cardioids. There are a few patterns that are pretty common, and we can look at those very quickly here, but I think a lot of that investigation is better done in class. Hands-on is really key here. So I want to use the rest of the time in this video to talk about just a couple of things that I think will clarify the work that we're going to do in the rest of this section. One of those things, I'm going to use circles as my example here. One of those things that is that if you have something like r equals 3 cosine theta versus r equals 3 sine theta, remembering really kind of as a mnemonic that x equals r cosine theta and y equals r sine theta. Cosine is an x thing. So this cosine graph is going to hug the x-axis. And this sine graph is going to hug the y-axis. Now I'm just sketching them here. I don't have a scale on my axes, so I don't really know what the diameter of the circles are. But that's okay. I'm just kind of trying to make a point here. Remembering these two things will help us in this case. And this is true with things like r equals 5 minus 5 cosine theta. Actually, I'm going to go with plus for right now. And r equals 5 plus 5 sine theta. You don't need to memorize these shapes, but sometimes it can be handy. These are going to look like, the cosine graph is going to look like this, and the sine graph is going to look like this. Again, the scale is kind of irrelevant here. I'm just trying to make the point. This sine graph is an x thing, and this cosine graph is a y thing. Let's see what happens if we scooch these up a little bit. Give myself some more room. Oops, that's not going to work. All right, what if I wanted to graph r equals negative 3 cosine theta? And I'll take one of each. I'll take one from here and one from here. And r equals negative 5. Actually, no, that's not quite how that one works. 5 minus 5 sine theta. Well, in this case, it's a cosine, so it's an x thing, but it's negative, so it's going to go this way. This one's just a circle, so it's going to look something like that. That's just my axis. For this one, it still has the form, the equation is the form of cardioid, but it has a negative in front of the term that has the trigonometric expression in it. So 5 plus 5 sine theta went this way. This one is going to go this way. And that's pretty much it. There are lots of other shapes, but we'll take a look at those in class, and we'll look at graphing them, and we'll look at mnemonics for remembering how many parts there are and what direction they go and all that kind of stuff. There's a summary chart. We'll look at that. Summary of curves at the very end. But that's all I want to do in the video for this subsection, and that's the end of this section. So this is the end of polar coordinates. In our next video, we're going to be looking at something called parametric equations.